So we've decided to do one lecture, one recorded lecture per chapter. So this will be the chapter 2 lecture, and I'm going to go over some of the concepts that I think are the most important. Okay, that doesn't mean I'll cover every single concept that you'll need to know. Okay, but I will cover most of them, most of what I think is most critical, and a lot of the concepts that will help you to understand other concepts in the chapter. And I'll try to make this efficient. I don't want to dwell too long. The book will have a lot of detail, but I want to just touch on them to make sure that you understand those core critical aspects. Incidentally, this chapter is about matter and change. And as you can see in this first picture, all of these changes just happen to be chemical changes. Okay, we'll talk about how to tell the difference between a chemical change and a physical change a little bit later on. First of all, as we get into these concepts, we're going to have a few terms that we use as we go along. And the terms are very helpful to make sure that we're really clear about what we're talking about. The first terms are extensive properties versus intensive properties. Okay? Now, extensive properties are properties that depend on the amount of something you have. What I'm saying there is essentially if you have more of something, that will change your measure or how you describe that extensive property. And if you have less of something, that will also change that extensive property. Okay? So an example of an extensive property is, a simple example is mass. Okay? So mass, obviously, the more you have of something, the greater its mass will be. Mass is the amount of matter contained in something. So obviously, when you have more of that substance or that object, you're going to have greater mass. Okay, so mass would be an example of an extensive property. Now, an intensive property does not change no matter how much you have of the substance. So as you can see here, we have a very small gold nugget, a larger one, a larger one, a larger one. As we go along, they get larger and larger. And that is an example of this is kind of a visual showing what we mean by intensive property. So an example of an intensive property would be density. I'm going to put that right up here. Density is the mass of something divided by its volume. Okay, so as obviously the mass goes up as we go along, but the volume also goes up. So when we take the mass divided by volume, it will always be the same no matter how much of that substance we have. So density is an intensive property. All right, now we're going to go through and just give a few examples of different properties, and then you'll help me, hopefully as you're following along, you'll help me decide which of these categories they go into. Let's put down our first ones we already know. So extensive properties are mass. That's extensive because the more of it you have, it changes the mass. Okay. Now an intensive property we talked about is density. In other words, in the case of gold, which we saw on the previous page, no matter how much gold you have, if it is pure gold, it will have the same density. Okay. In fact, density is one of the ways that they identify gold. If you go up in the mountains and you say, hey, I have found a new gold nugget, one of the best ways to decide if it actually is a gold nugget is to measure its density. Find out its volume, divide it by or find out its mass, divide it by its volume, and it should match up with the well-known term or the well-known measurement for density that you can find in a textbook. And if it does, then you just may have struck gold. If it doesn't, you might have something else like fool's gold. And that's a great way to figure that out. Okay, another couple of examples here we're going to run through. Temperature. Okay, now take the example of a big pitcher of water. Okay, is the temperature going to change depending on whether you have a cup of it or whether you have the whole pitcher? Okay, it won't change the temperature. So temperature is not dependent on the amount of something you have. So therefore, temperature would be an example of an intensive property. Okay, a couple of other ones. Length. Does length make a difference does length change depending on how much you have of something? Absolutely. Length is an extensive property. Okay, another one is volume. Does volume change depending on how much you have of something? Of course it does. If you've got more of it, it will have a greater volume. So volume would be an example of an extensive property. Okay, now let's look at a few others. Color. Does color change just depending on how much you have of something? No, the color is going to be the same. If it's purple, if you have a little tiny piece or a very large piece, it will still be purple. So I'm going to put color over here. Okay, another one I'm going to put over here is hardness. Okay, hardness is not dependent on how much you have of something. And we'll mention also here total charge. Okay, your total charge, the more you have of something, if you have something that has a charge, the more you have of it, the more total charge you'll have. Okay, that's not something, that last one is something you really don't have to worry about yet, but it's just so that you understand that that would be an example of an extensive property. All right, the next concept that we'll go into is states of matter. Okay, states of matter are best thought of with one of the most familiar examples, which is water. Okay, we have solid, we know as ice, we have liquid, and then we also have gas, which is water vapor. Okay, and the keys here are in a solid has a definite shape, a definite volume, and a definite mass. Okay, think of an ice cube. Okay, that ice cube holds its shape. Okay, obviously you could crush it and do different things to change that shape, but in general, when it's just sitting there, that ice cube is going to hold that shape that it begins with. All right. It also has a definite volume. Okay, you could use your mathematical skills and measure the height, the width, and the depth and figure out the volume of that ice cube. And it also has a definite mass. Okay, it has a certain amount of matter in it, and that isn't changing. Okay. Now we get to a liquid. A liquid is a little bit different. A liquid, all of the little molecules that make up water slide past each other. And it makes it so that a liquid will adapt to any shape that you put it in. So it doesn't have a definite shape. An ice cube is going to stay in that cube shape even if you put it into a different container. Whereas a liquid, if you put it in a cup that's shaped like Mickey Mouse, the liquid is going to assume that shape like Mickey Mouse. So it does not have a definite shape. The shape will change depending on the container you put it in. But it does have a definite volume. Okay, it will only take up a certain amount of that container, whatever that container is. And that's shown here in the picture. Obviously, the liquid is only taking up the first little bit of this container. Okay, that's because it has a definite volume. That volume is not going to change. It also, just like solids, has a definite mass. Finally, a gas. Okay, the gas form, like water vapor, it does not have a definite shape. Okay, it will assume the shape of whatever container it's in, kind of like a liquid. But something different about a gas is it does not have a definite volume. It will take up the entire space of whatever it occupies. So if you put it in a very large container, it will spread out to where it is taking up the entire volume of that container. Okay, so if it's in a room, those little water molecules that float around and bounce off the walls are going to take up that entire room. Okay. Now the only thing that we can say that it does have is it does have a definite mass. Okay. So it still has a definite mass, which means it has a definite amount of matter. Mass is never created or destroyed. Okay. So even when a substance turns into a gas, it will still have a definite mass. Now, let me just give one other way to think about each of these. A solid is much like a group of soldiers that are very organized, that stay in their places, that don't move around. A group of soldiers standing at attention. Okay, it takes on this crystalline structure. Okay, now a liquid is a little bit more like kids in junior high. Okay, if you put them in there and you have them in lines, they're going to be moving around and sliding past each other and jumping from one line to the next. Okay, they'll probably take up all of the area that they're in, at least along the ground. Okay. Now a gas is a little bit more like a bunch of kindergartners in a bouncy house. Okay. They not only slide around, but they also bounce off the ceilings and the walls and the sides of that container. They take up the entire thing, even vertically as far up as they can go. So that's one way to think of a solid, a liquid, and a gas. Speaking the language, we've talked about some terms already. We'll talk about a few more here. An element is something that's made of a single type of atom. Let's give an example here. Au. Okay, Au. I don't know why it does that. Let's try that again. Hold on just a second here. Okay, so Au. Okay, Au is gold. And you might be wondering why it's called Au. It's because in Latin, where the periodic table is based on, Au is short for aurum, A-U-R-U-M. Aurum is the word used for gold in Latin. So the symbol Au is based on that. Okay? But when it comes to an element, if we talk about pure gold, what we're saying is that this gold nugget that we have is made up of all Au atoms. Okay, nothing else. Okay, another example here, oxygen. Now, the symbol for oxygen is an O. All right. But here's something important about oxygen. When I say we breathe oxygen or there's oxygen in the air, okay, I'm not referring to single O's flying around. Instead, oxygen is only found in this form, okay? When oxygen, the oxygen element, okay? The oxygen element is only found in this form, O double bond O. Two oxygens bound together, okay? When we write this, we always talk about O2, okay? The 2 means there's two oxygens that are bound together, and that is how you find elemental oxygen. You do not find it as single O's flying around, all right? Both of these are types of elements. Secondly, a compound. A compound is a substance made of at least two elements which are bonded together chemically and have a definite proportion of atoms. Let's go to our simple example we've already talked about. O bond H bond H. We all know that this is an example of water. Okay, so it has two different elements involved in it. It's got oxygen and hydrogen. So we wouldn't call water an element because it has two different types of atoms chemically bonded together. Okay, and something else important is that it has definite proportions of atoms. Okay, the proportion here is two hydrogens to one oxygen. Okay, that's not a 10, that's saying one oxygen. Okay, so there's two hydrogens to one oxygen. The ratio is 2 to 1. All right, and you can see why that's the case because these compounds always come in threes like this, and it's always two hydrogens to one oxygen. And so that proportion is always going to be the same. Finally, or the next one is a molecule. A molecule is when you have two or more atoms joined together by chemical bonds. Okay, so there's a lot of examples of molecules. I'm going to give one right here. We've already given one above. OC double bond O. Okay, this is CO2. It's carbon dioxide that gets a lot of press. We'll talk more about that later. But carbon dioxide is an example of a molecule with two or more atoms joined by chemical bonds. Okay, now these don't have to be different types of atoms. Let's give the example that we had above of oxygen. This is actually a molecule where you have two oxygens bound to each other. Okay, that also is a molecule. So you could have a molecule that has two of the same atoms bonded to each other. That would also be a molecule. It's essentially when you have some bonds that are linking atoms together. And finally, a substance. A substance is kind of a broad term that we use, but a substance is just, it's some type of compound that cannot be separated using physical properties. So obviously, water would be an example of a compound. CO2 would be an example of a substance. These are all examples of substances. Substance is a word that we use a lot, but it's essentially a substance. A substance is just something that cannot be separated further without using chemical reactions. Okay, so we'll talk more about that momentarily. All right, mixtures, two or more substances that are mixed together. All right, there's a whole bunch of different types of mixtures. Okay, a mixture could be as simple as sand mixed with marbles. It could be as simple as wood chips mixed with rocks. Okay, like you see at playgrounds a lot. all of these are examples of mixtures. So here are some specific types of mixtures. Okay, first of all, we have homogeneous mixtures. Homogeneous mixtures are mixtures where the two substances are mixed very evenly. Okay, the two substances that you have in Kool-Aid are sugar with a little bit of food coloring and some minor amount of artificial flavor that's mixed into water. Okay, the key with a homogeneous mixture is it's very evenly mixed. Any portion that we sample of this drink will have about the same amount of sugar in it as any other portion, at least per volume. It will have about the same concentration of sugar, okay, because that sugar is very evenly mixed. Maybe even better example of a homogeneous mixture is what's shown here. It has not become yet a homogeneous mixture, but this is salt being poured into water, okay? And once that's poured in and then you mix it together, it'll be extremely evenly mixed. In fact, when you look at that salt water, you will not see any particles in it, okay, because they're so small and so evenly mixed that you can't see them anywhere. But if you tasted it, it would all taste about any part you tasted of that water would be just about as salty as any other part you taste. Okay, so salt would be a good example of a homogeneous mixture. Okay, the next concept, heterogeneous mixture. Okay, now I know different people say this differently. I just say heterogeneous. There might be some other ways you could pronounce it, and that's completely fine. The key though with a heterogeneous mixture, a good example of it would be if you take water and mud or dirt and you shake it up, okay, and you have it all mixed together. Because what will happen if you notice there are some darker portions of this, there's like a chunk up here, there's a bigger chunk down here, okay, those are examples of with a heterogeneous mixture, that means it's not perfectly evenly mixed. Okay, you might have a chunk on one side, you might have a little particle on another side. And also you'll notice here that with this heterogeneous mixture, it starts to settle out, okay? And eventually you get to over here where all of your mixture is sitting on the bottom. Now, a heterogeneous mixture doesn't have to be able to settle out, but usually, like in the case of mud, they often will, okay? And it doesn't evenly mix, it eventually settles out of the water, and that would be an example of a heterogeneous mixture. Okay. Now, a colloid is a little bit different, and the thing that is different about a colloid, first of all, is a type of homogeneous mixture, but it's different from something like salt water because the particles that are mixed in to the larger to the water, the particles that are mixed in are much bigger, okay? So a good example of a homogeneous mixture would be milk. Okay, milk it's homogeneous, the milk's kind of evenly spread throughout the water, but the particles are much larger, so you can see them. You can't see through milk. It's not transparent. Paint would be a good example. Blood is a good example in the sense that blood has red blood cells that are, if you have a sample of blood, they're generally evenly mixed, but they're much larger than you would expect from something like salt water. So colloid, it's a homogeneous mixture with large particles dissolved. We'll put it that way. Yep, switch to the next one there. Okay, a suspension is slightly different from a colloid. The thing that's different about a suspension is that a suspension only stays mixed together for a short amount of time. In fact, a suspension generally would be a category within a heterogeneous mixture. Orange juice would be a very good example of a suspension because with orange juice, if you let it sit for a while, as you can see in this picture, you let it sit for a while and a lot of the little particles in the orange juice will settle out. That's why the bottles that you buy with orange juice will say to shake well before opening, okay? Because that will mix all of those particles and it'll put them back into suspension, whereas they had previously settled out of suspension. So that's an example of a suspension. So those are the concepts you need to know: homogeneous, heterogeneous, colloid, and suspension. The most important ones are just knowing what a homogeneous mixture is and a heterogeneous mixture. If you understand that, you're kind of good to go on these concepts. All right, on to physical and chemical changes and how to tell the difference. We've talked about these a little bit in class, so some of you will already know what we're talking about. But I want to get down to really specifically what a chemical change is and a physical change. All right, and then later on we'll expand on this. I know the book gives a very simple definition, but I kind of find sometimes if you give too simple a definition, it becomes more confusing than if you sort of give the the full version of the story. Okay, so a chemical change is any change. Oh, sorry, we just hit the button there. Any change that rearranges atoms and bonds. So any change that rearranges atoms and bonds. And here's a key here. Forms a new substance. Okay. All right, keeps on switching me. Okay, then a physical change is obviously just the opposite. Changes that do not involve rearranging bonds and atoms. All right, go back there. All right, so we'll talk about some examples of each of these, but that's the key to think about. With a chemical change, you have a new substance that you've created through that chemical reaction. In a physical change, you don't have new substances. Okay, so let's go through some examples. So here are some examples. It's a physical change if it changes the shape or size or it dissolves. Okay, we already talked about dissolving salt in water. Okay, so we have our cup of water here. We put some salt particles down here, and they all dissolve and they evenly mix into that salt water. But we have not created a new substance. Okay, we've simply changed the way it looks because it's now dissolved in the water, but we still have salt and we still have water. We don't have anything new. So salt water would be an example of a physical change because it's dissolving. Okay, if it's just changing the shape or size, that's kind of obvious. That's, for example, if you take a piece of coal and you crush it up, all right? You haven't created a new substance. It looks different, okay? It may even have a different, it may even, it may have a different size, may even have a different feel in certain cases, but it's still coal, okay? So that would be a physical change, all right? It's also a physical change if it changes phase by freezing, boiling, evaporating, or condensing, okay? So these are phases changing between solids, liquids, and gases. Any phase change, freezing obviously, and these are terms that are actually good to make sure you understand. Freezing, boiling, evaporating, and condensing. Freezing means that it's going from liquid to solid. We know that from water, okay? So when something changes, when water changes from a liquid to solid, yeah, it looks different, it feels different, but it's still water. You have not created a new substance. Therefore, it's a physical change. Chemical changes. Chemical changes are they're changes in the way the molecules link up and they make new substances. This is essentially saying the same thing I said earlier, just phrased a little bit of a different way. Here's some examples of chemical changes. It's a chemical change if it burns, okay? Burning is, let me give you an example here. If we take methane, CH3, plus, sorry, it's actually CH4, my mistake there. CH4 for methane plus oxygen is going to produce CO2 plus H2O, okay? This is a common formula for anything that burns, okay? Most things will look a lot like this. Methane is one example of something being burned, but we could also use the molecules that make up wood, which would be something like methane, but they'd be much larger. They'd have a lot more carbons and a lot more hydrogens, but generally it'd be carbons and hydrogens. Okay, that would be an example of a chemical change, because if you look here, and when I draw this out, this is called a chemical formula. These are like our ingredients. This is what we start with. Okay, they're called reactants. Okay, these are our products. This is what we end up with. As you can see right here, we have new substances. These are substances that we never had there before. Okay, so temperature. So these are some ways that we can know that that a chemical reaction is happening. So if the temperature changes without heating or cooling, so if all of a sudden, spontaneously, the temperature increases when you mix two things together, that's probably a chemical change. Let me give you an example. The hand warmers that you see, okay, those are made up, some of those are made up of a lot of iron, little filings of iron in them. So when the iron, when you take it out of its package, the iron mixes with oxygen, and that causes a chemical reaction. It results in iron oxide, is a new chemical that's formed, and so therefore the temperature will increase because that is releasing energy as that chemical reaction happens, and that's what keeps your hands warm. So that would be a great example of a chemical reaction because it releases temperature. That's an indication that a chemical reaction is happening. It's a chemical change if it bubbles. Okay, here's a great example when we have this. This is a mixture of something called sodium bicarbonate, and I'm just going to write it up here. Oh, look at this. This is getting a little annoying with my pen here. For some reason, it puts these NaHCO3. That is baking soda, sodium bicarbonate. So don't worry about the details of this right now. I don't know why it keeps doing those funny little lines, but NaHCO3, that's sodium bicarbonate plus acetic acid. That's going to be CH3COOH. Acetic acid is the same as, this is baking soda here, and then acetic acid is vinegar. Okay, and when we mix these together, we're going to get a product. One of the products we will get is going to be CO2, which is carbon dioxide. And that's what's causing all of these bubbles. Okay, you know this science experiment you've done a million times. The bubbles are being caused by carbon dioxide that is forming. We didn't start with carbon dioxide. We only started with sodium bicarbonate and vinegar. And then one of the products, and there are multiple products, we won't go through all of those right now, but one of the products is carbon dioxide gas. Okay, so if a gas forms as part of the reaction, then that is usually an example of a chemical change. And also if there's a change in color, or if it forms a precipitate. Okay, so change in color, you know, we of course know if there's a spontaneous change in the color, that is often an indication of a chemical change. It isn't always. I'll give some other examples later on. But when it forms a precipitate, what happens here is sometimes it'll look like you could take something that looks like salt water, you could mix it up with something else that also looks like a clear water. You mix them together, and then all of a sudden a substance appears, just like this yellow substance here. Okay, that's called a precipitate. Okay, and that means that even though the previous two substances were soluble or could be dissolved in water, this new substance no longer could be dissolved in water. So all of a sudden it appears and it starts to precipitate, which means it starts to fall to the bottom of that test tube, and that is called a precipitate. And that's a good example that a chemical change has taken place. All right, so let's talk about this. On the side, you can go through and tell us whether each of these types of changes are physical changes or chemical changes. Except we have the answers already there. That doesn't help much. I should have covered them up, but we'll go through them anyway here. So we tear up paper. Obviously, that's a physical change. We had paper before, we have paper afterward. We do not have a new substance, therefore it is a physical change. We mix salt and water. We already talked about this one. We know that's a physical change, okay? Even after we mix salt and water, yes, it looks different. Yes, its form is different in the sense that now it's dissolved in the water. But before the reaction, we started with salt and water. After the reaction, we still have salt and water. Therefore, we have just a physical change. We have not rearranged any of the molecules. We have not rearranged any of the bonds and atoms, and we have not created any new substances. Therefore, we have a physical change. Okay, we burn paper. Okay, that is a chemical change. Okay, because burning paper creates a new substance. The black substance that you see when you burn paper, that is part of that new substance. Okay, and it also creates water and CO2. Okay, that's something you may not be aware of, but one of the things it does create is CO2. We could talk about that more later. If we evaporate salt water, okay, so what happens, this is common if you've ever seen the Great Salt Lake as you go into Utah. You'll see these large fields of salt. That's because they used to be part of a lake and the water evaporated and left the salt behind. Okay, that is an example of a physical change. Okay, because before that change, there was water and salt. After that change, there was still water and salt. The water has evaporated, the salt has been left behind. But there's been no rearranging of bonds and atoms, and there have been no new substances created. All right, mixing vinegar and baking soda, we just talked about that one. That one is obviously a chemical change because we form the gas CO2. There was no CO2 present previously, and now that the reaction has taken place, there is CO2. So that is an example of a chemical change. All right, well, that concludes the slideshow, and hopefully that will summarize everything you need to know in Chapter 2. But if you have additional questions, please come ask me. And it's possible if there's something that's an error in the video, let me know and we can make a note on it so that people can know what the error is, and we can put a note there so that we can clarify it and confirm it. So see you next time on the next video. Bye.